Hello everyone, welcome back to the channel. I'm Saurabh, MSc in Photogrammetry and Geoinformatics with practical experience in GIS, remote sensing and geospatial data analysis. On this channel, I share simple and practical knowledge about GIS, remote sensing and geoinformatics technologies. So, let's start the video. In today's video, we will clear up one of the most common confusions in geospatial science, GIS versus remote sensing. Many beginners think they are the same thing because both use maps, satellite images, and location data, but they play different roles. Remote sensing mainly observes and measures the Earth from a distance. GIS mainly organizes, analyzes, and communicates geographic information so that people can make decisions. By the end of this video, you will understand the difference clearly and also see why modern projects usually combine both. Before we go deeper, let us set the learning goal. This video is made for beginners, students, and early career professionals who know what a map is and may have seen satellite imagery but may not yet understand the technical differences between GIS and remote sensing. The main idea is simple. GIS is an analysis and decision making system, while remote sensing is a data acquisition and measurement approach. We will define both terms, compare their data types, scale, resolution, accuracy, and outputs, and then look at the real workflow where both are used together. Let us start with GIS. So I have already made one video. If you want to clear your concept about GIS, you can first see that video, then you will get the clear idea what is the background and what is the concept of GIS. So GIS means Geographic Information System. A GIS is not just software for making beautiful maps. It is a complete spatial information system. It can store location-based data, manage different layers, analyze relationships, and communicate results through maps, dashboards, and web applications. For example, in one GIS project, you can combine roads, rivers, buildings, and land uses, also different spatial data, for example, population, elevation, and flood zones. Then you can ask practical questions. Where is the highest risk? What is nearby? Which road is affected? Or where should we build next? This is why GIS is very important for planning, disaster management, transport, environment, and many government services. Now let us understand remote sensing. Remote sensing means collecting information about the earth without touching the objects directly. So here you can see different kinds of sensors. This is usually done by satellites, aircraft, drones, or special ground-based sensors. These sensors measure energy reflected or emitted by the earth. Optical sensors capture visible and near infrared information. Radar sensors send signals and measure the return. Thermal sensors measure surface temperature, and LiDAR sensors create very detailed elevation or 3D information. The result is usually raster data, meaning pixels with values. These values can later become vegetation maps, water maps, temperature maps, elevation models, or land cover classifications. The easiest way to compare them is by role. GIS is mainly by the environment where geographic information is integrated and analyzed. Remote sensing is one major way of gathering geographic information. Remote sensing often creates the input data and GIS turns that input into a useful decision product. For example, remote sensing can detect flood water from a satellite image, but GIS can combine that flood layer with roads, houses, hospitals, and population data to understand who and what is affected. So, the key message is remote sensing measures from a distance and GIS adds context, analysis, and communication. Another important difference is how we judge quality. In remote sensing, quality is often discussed using four kinds of resolution: spatial, spectral, temporal, and radiometric resolution. Spatial resolution means the pixel size. Spectral resolution means how many wavelength bands the sensor records. Temporal resolution means how often the same area is observed. And finally, radiometric resolution means how sensitive the sensor is to differences in energy. In GIS, quality is discussed differently. We look at the positional accuracy, attribute accuracy, completeness, topology, metadata, and whether the data scale fits the question. So remember, a high resolution satellite image is not automatically a good decision map. Both remote sensing and GIS require validation and careful interpretation. Let's show how GIS and remote sensing work together in modern workflow. First, data is collected using satellites, drones, aircraft, or modern sensors. Second, the imagery is pre-processed, corrected, mosaicked, or cleaned. Third, useful products are derived, such as NDVI for vegetation, water extent for flood mapping, temperature surfaces, and land cover classes or change detection layers. Fourth, those outputs are brought into GIS together with administrative boundaries, roads, buildings, populations, or infrastructure. Finally, GIS is used to analyze exposure, prioritize action, and publish a map, dashboard, report, or alert. In real projects, the final output is rarely just an image. It is usually a decision product. Now let us look at the real examples. In flood mapping, radar remote sensing is very useful because it can detect water even when clouds block optical imagery. But GIS is needed to identify which roads, schools, hospitals, and communities are affected. In agriculture, multispectral imagery can show crop health, but GIS links that information to field boundaries, soil data, irrigation systems, and yield zones. In urban planning, remote sensing can detect heat islands or land cover change, while GIS adds zoning, transport networks, and population information. In environmental monitoring, satellite change detection becomes useful only when GIS connects it with management zones, protected areas, and policy actions. The software ecosystem is nowadays also changing. Traditional GIS tools include ArcGIS and QGIS, but modern projects also use spatial databases, WebGIS, cloud services, and APIs. Remote sensing tools include Snap for Sentinel data, ENVI, ArcGIS Image Analyst, Google Earth Engine, and OpenEO. Public data sources include Landsat, Sentinel-1, Sentinel-2, MODIS, VIRES, and harmonized Landsat Sentinel products. Today, cloud native standards such as Stack and cloud optimized GeoTIFF are becoming very important because they help users discover and process very large Earth observation datasets without downloading everything locally. AI is also becoming more common for classification, object detection, and change analysis. Let us correct three common misconceptions. First, remote sensing is not just pretty satellite imagery, it can produce quantitative information such as vegetation indices, land surface temperature, elevation, deformation, flood extent, and land cover classes. Second, GIS is not just map making software. GIS supports spatial analysis, routing, suitability modeling, dashboarding, exposure analysis, and decision support. Third, one does not replace the other. In most strong geospatial projects, remote sensing provides observation and measurement, while GIS provides integration, context, and analysis. A good professional should understand both, even if they specialize more in one side. Let us finish with simple summary. Remote sensing asks what can we observe or measure from a distance. GIS asks how can we integrate location-based information to answer a real decision questions. Remote sensing gives us repeated wide area evidence. GIS connects that evidence with people, places, assets, and actions. So, do not think of GIS versus remote sensing as a competition. Think of them as two connected parts of the modern geospatial workflow. If this video was helpful, subscribe to the channel for more beginner-friendly GIS, remote sensing, and geoinformatics lessons. Thank you so much.